Okay. All right, and we are back. All right. So this we should be able to finish out this section. All my other classes we were able to finish this with the time allotted for the day. Finish out this section. So we should be able to do the same thing. Yeah, we got plenty of time. We can do it. So we're gonna knock it out. This is gonna be the last of the new material. Mini celebration, right? Okay, let's go ahead and finish it. So the last section comes from chapter 6, further topics in algebra. This comes from section, okay, thank you for that. Let's try this again. So this is a last section and for the, totally threw off my rhythm. So this is going to be the last of our new material. Section 6.4, system of equations in two variables, okay? So yeah, let's just knock it out. So this is section 6.4, system of equations in two variables, okay? And let's see, so we have some definitions. A set of equations with common variables is called a system of equations. If each equation is linear, then the system is called a linear system of equations. If at least one equation is nonlinear, then it's called a nonlinear system of equations. Here's a system of two linear equations and two variables, right? So every time we have an unknown, we need an equation. We have two unknowns, we have two equations, so we can solve, right? A system of equations is sometimes referred to as a set of simultaneous equations. A solution of a system of equations in two variables, x and y, is going to be an ordered pair, a comma b, such that, come here, come here, come here, come here, come on. Malachi, come here. Come here. Come here. Go to bed. Go to bed. And you can stop losing your mind while I'm trying to. I know. It's okay. Here. Here. You can use that. Boom. Your favorite space heater. All right. Here, lay down. Lay down right there. All right. So again, the solution to the system basically is an ordered pair that makes the solution true, right? So when we plug in the ordered pair, it should make all equations true. Okay, let's see this in action. I feel like this is easy to see. So we're asked to verify that the ordered pair 3, 1 is the solution of the system, all right? So all we're going to do, as soon as I can find my pen, all we're going to do is plug in when x is 3 and y is 1. Wow, the thing is super hot. Hang on. Let's try this. Maybe here. Okay, so to verify that the order pair 3, 1 is a solution, we're just going to plug in when x is 3 and y is 1, right? So then for the first one, we're going to have 2 times 3 minus 1, that's going to be what? 6 minus 1, which is 5. So that checks out. The next one is going to be 3 plus 2 times 1. That's going to be what? 3 plus 2, which is still 5, which is the desired result there as well. So we verified that the order pair 3, 1 is the solution of the system. Okay. Let's try the next one. So I think we did all that, and we showed that it worked in both equations. So then we actually use the graphical method to solve the system. Okay, so we're going to graph both of these. Okay. So from equation 1, if we solve for y, we get y equals, and let's just do that one in blue. We're going to do that one in blue. Okay. Y equals 2x minus 4, right? And then we'll do the next one. I guess we'll do red, right, for equation 2. So again, what I'm doing this one in blue. And this one I'm going to do in red. Okay. So if we solve for y there, initially we're going to get 3y equals negative 2x plus 12. Let me thicken it up just a little bit. Divide both sides by 3, y equals negative 2/3 x plus 4. Right? So let's graph these two. Oh, okay, I can do this. Let's do paper. Let's do some graph paper. Where's my, here it is. Okay. So we'll do the positive x in this direction. We'll do positive y in this direction. Let's go, let me see, x. Okay. So if we go about 6 in every direction, let me center this a little bit better. Okay. 1, 2, 3, 4, 5, 6. And let me get a copy of these tick marks. Copy, paste. That looks good. Paste. Okay. Let's label this. So this is like 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6. 4, 5, 6, 7. This is the origin. 2, 3, 4, 5. These are negative values. These are negative values. Okay. Check the time. So now let's graph the equation 1 in blue. So the y-intercept is negative 4, and then the slope is 2. So if we go, and then I'm gonna change my paper to this one. So the slope, we go up 2 and right 1. We can put a point. Let me go the other direction as well. Down 2 and left 1. So up 2 and right 1. Up 2 and right 1. Up 2 and right 1. Up 2 and right 1 is there, right? If we connect these with a straight edge, okay, we get a graph like this. Okay, so that's for the blue one, and I'm just being super nitpicky at this point. I just want to do that instead. I'm just doing it because I can. Like that. Boom. That's good enough. Okay. So then let's graph the red one. So the y-intercept there is 4, and the slope is a negative 2/3. So we go down by 2 and right by 3. 1, 2, 3. We have this point. Down 2 and right 1, 2, 3 is this point. Let me see if I go down 2 and right 1, 2, 3. We should have this point. Let me go up 2 and left by 3. 1, 2, 3 is this point. So now if we connect those with a straight edge, we get that along with this. And then just to be consistent, I'm going to get rid of that. This band. So then we get this, right? So we're actually solving it graphically. So now it's clear that these two graphs cross. This is the point 3, 2. So the solution, they cross at the point, actually, red and blue makes this color. So they cross at this point 3, 2. Right? So our claim is that the solution to the system is the, I'll fix all that. Style, we need the fill to be none. Okay. So we got, and let's just do what I was doing. We can make it bigger. Okay. All right. Oh, so then we want to verify that this works, right? So let's check. So if we say 2 times 3 minus 2, that's going to be what? 6 minus 2, which is 4, which checks out. Again, we're checking right now. Then if we say 2 times 3 plus 3 times 2, that's going to be 12, which is also the desired result there as well. Right? So graphically, the solution is going to be where the graphs cross. Okay? Did we use the same colors in the same way? We did our colors reversed, so that's okay. Okay? And we check, they both work, so we're good to go there. Man, it's just got like dark all of a sudden. It's still light out, but it's like super dark in here. Okay? So then now we want to explore solutions of a system of equations. The solution set of a system of two linear equations and two variables can be classified in one of the following ways. We can either have one solution where the graphs cross once. We could have no solution where we have parallel lines and the graphs never cross, so we have no solution. And then we can have infinitely many solutions where basically one line is a multiple of the other, and so one line is on top of the other, and so we have infinitely many solutions, right? So in this example, we're asked to solve the system, and we're asked to solve it with the substitution method. So let me add a page, and I'm going to get a copy of this original. Oh no! Oh, it's almost 5:55. So I'm going to take that. Come on, you are bugging. Delete. I just want from here. Here's fine. I'll put it right here. Of course, that's what I always do. Okay. We're going to solve. Let me reboot you because I don't like the rhythm. Uh-oh. It should be this one. 424. It should be this one. We left off. Okay, much better. All right. Let's go on paper. Okay. So I think here we're asked to solve this with the substitution method, right? So in the substitution method, this technique, what we're going to do is solve for one variable from one equation, and then take that and plug it into the other equation. So to me, it looks like it's easier to solve for y in equation 2, right? So here's a copy of the original equation from number 2. And then if we add 2x to both sides, we get y equals 2x plus 9, right? Then we can take this and plug it into equation 1. So we're going to have 2x minus 5 times y equals 3. But what's our y in this case? Our y is 2x plus 9. And then now we have one equation, one unknown we can solve. Again, every time we have an unknown, we need an equation. We started with 2 unknowns, so we have 2 equations, so we're good. At this stage, we have one equation, one unknown, so we can solve. We can distribute this negative 5. We get this, minus 10x. What is that? Minus 45 equals 3. Is that negative 8? Am I missing something? Add 2x plus 9, 2x Okay, let's keep going. So 2 minus 10 is going to be what? Negative 8 equals, if we add 45, we get 48. X equals negative 6. Right? So if x is negative 6, then our y is going to be equal to 2 times negative 6 plus 9. It's going to be a negative 12 plus 9, which is negative 3. So our claim is that the ordered pair negative 6 and negative 3 should work in the original. Okay, so let's try negative 6, negative 3 in the original. So we're going to do a quick check. 2 times negative 6 minus 5 times negative 3 equals 3. That's going to be a negative 12 plus 15. And let's actually get rid of this 3 over here. Equals 3, which is our desired result. And then for the next one, we're going to say negative 3 minus 2 times negative 6. That's going to be equal to negative 3 plus 12, which is 9, which is the desired result we're looking for there as well. Okay? So this negative 6, 3 worked in both. Let's go to view. Okay? So then we have a typed version of all the work that we just did. Okay, let's give this one a go. So we can still use the same method here, where we substitution method, where we solve for one variable and then plug it into the other. So it looks to me like it's easiest to solve for y from the first one. So if we solve from y, we're going to get y equals negative x plus 3. Then we take that and plug it into the other equation. We have this 2x plus 2 times our y, which is negative x plus 3, which should equal 9. And if we solve, we get 2x minus 2x plus 6 equals 9. Ultimately, we get what? 0 equals 3. This is false. Right? So then we say that there's no solution or empty set. This is called the null set. It means no solution, or the empty set, you know, null set, right? So no solution, contradiction. So that means we should have two parallel lines, right? Non-vertical parallel lines. So they never cross, so no solution. Okay. All right, so we can use the same method. Let's solve. I'm going to solve for y in the second equation. So if we add and add, we get y equals negative 2x plus 6. Then take this and plug it into equation 1. So then we're going to get 4x plus 2 times this negative 2x plus 6 equals 12. Let me hold up. Okay. So then if we distribute, okay, we get this 4x minus 4x plus 12 equals 12. Ultimately, we get 0 equals 0. All right, which is true. So notice our variables cancel. We finish with the true statement. So that means we have infinitely many solutions. And no matter what x we choose, y is going to take on the form negative 2x plus 6, right? So we have infinitely many solutions taken on this form. Style, infinitely many solutions taken on this form. Okay. And you can choose, like, choose your favorite x, find the corresponding y, and it's going to work. It should work in both equations. So you see it here. Okay, so we saw some demos doing the substitution method. Now we want to explore another technique for solving a system of equations, which is called the elimination method. So let me get a copy of this. Okay. So let's do a demo on the elimination method. Let's start by getting a copy of the original. We have this 2x plus 3y equals 21, and then we have this 3x minus 4y equals 23, right? So we want the variables to be the same but have opposite signs. So I'm going to focus on the y. I'm going to have it y. I'm going to get it to where y can be the same number with opposite signs. So to do this, we can multiply any row by any non-zero number, right? So I'm going to multiply the first row by positive 3 and the second row, the first row by 4 and the second row by 3. So we can multiply this row and every term in it by 4. And then we're going to multiply this one by 3 to generate our desired result. On top, we're going to get 8x plus 12, 1 through 12, 12y equals, what is it, 84. On the bottom, we get 9x minus 12y equals 69. If we add these together, now we add the two equations together, we're going to get 17x equals 153. Hey Siri, what's 153 divided by 17?
Just a moment. Working on that. Something went wrong. Please try again.
Try one more time. Hey Siri, what's 153 divided by 17? No?
Just a sec.
All right, we take it too long.
9.
Thank you.
One more moment.
Looks like somebody can get a job and somebody else is fired, Siri. Fired. Okay, anyway.
Sorry, something went wrong. Please
So,
try again.
so we get 9, right? Let me see. 90 plus 63, 153 sounds good, okay? So now, if this is our x, then we can take it and plug it back into either equation to solve for y. I'm going to plug it into the first one because it just looks more simple. So we're going to say 2 times 9 plus 3 times y, and we don't need the parentheses there. 3y equals 21. So then 3y equals, if we subtract 18 on both sides, we get what? 3 and y equals 1. So our claim is that the solution, the ordered pair is going to be 9, comma 1. It's going to be the solution to the system. Okay. Let's see. What's the time? Okay, let's just do a quick check to make sure this works. So 2 times 9 plus 3 times 1, that's going to be what? 18 plus 3 is 21, which is our desired result. And then 3 times 9 minus 4 times 1, that's going to be what? 27 minus 4, which is 23. Again, that's our desired result as well. Okay, let's go paper. Let's go view. That's seamless. Okay. And I think we have a typed version of what we just did. Okay. So in this next example, we're going to use a technique called U substitution, right? So instead of working with this directly, we're going to say let u equal 1 over x and let v equal 1 over y, right? So then that's going to transform the system into the following. We're going to have 2u plus 5v equals negative 5. And we're going to have 3u minus 2v equals negative 17. Okay. Let's see. So we can use the elimination method again. We want them to be the same. We want one of the variables to be the same, but have opposite signs. So I'm going to cancel out my v. I'm going to multiply the top by what? 5. And distribute a 5. I'm going to multiply the bottom by, nope, not 5. The top by 2. Top by 2. The bottom by 5. Right? Okay, that looks better. And distribute that 5. Okay. So then if we account for these changes, on top we get 4u plus 10v equals negative 10. We get 15u minus 10v equals 50 plus what, 35 is 85. Now if we add the two systems or the two equations together, we're going to get 19u equals negative 95. What is that, 5? 50 plus 45? I think that's 5. So then we get that u equals 5. So then if u is 5, I'm going to plug it into the first equation. So we're going to have 2 times 5 plus 5v should equal negative 5. That means that 5v is going to equal, if we subtract 10, we're going to get negative 15. Am I missing something? Yeah, there it is. That's what I'm missing. I think instead of 5, it's supposed to be negative 5, right? Right here. That's supposed to be negative 5. I already heard one explosion outside. Let me see. I don't know. I'm trying to decide if it was like a shot, if it was a firework. Man, oh man. We'll finish up this class and hopefully we'll see everybody on Thursday. We're almost done. All right. Hopefully, let me check something real quick. Yeah, looks healthy. Okay, let's finish this out. So we got to account for that change that we just made. So this is supposed to be 2 times negative 5. Okay. So that makes that a negative 10. Now when we add it, we get the desired property. Right? We add 10. 10 minus 5 is 5. So then v equals 1. Okay. So then let's kind of work over here. If u equals negative 5 and u equals 1 over x, and that means that 1 over x equals negative 5. So that means that x equals a negative 1 by 5. If v equals 1 and v equals 1 over y, that means that also equals 1, so that means that y equals 1. So then it sounds like the ordered pair is going to be negative 1 by 5, comma 1. Okay. So then we just want to check this ordered pair in the original. I think I'm going to just use a calculator for that. Okay, we are here. Fill that out. And then switch sides. All right. So we're going to say for the first one, 2 divided by x, which was, here, let me do this real quick. So I'm going to say negative 1 over 5. I'm going to store that. Can I store that as x? That might mess stuff up. Let me not do that. Let's just do 2 divided by negative 1 by 5. Plus 5 divided by what? 1? We should get negative 5. And then the next one, we're going to say 3 divided by negative 1 by 5 minus 2 divided by 1, and the answer should be negative 17. Okay? So we confirmed that this ordered pair works, and let's go on to the next one. Pretty sure you're okay, but I don't want you to overcook. I know you're not going to do it. Okay. I think we got all these results. We got that for x and y. All right, I think we might have one more. Okay. So this is the last one. Yay. Okay. Find the equilibrium point if the supply and demand functions for a new DVR are given by this system, where P is going to be the price in dollars and X is the number of units, right? So the equilibrium point is where the supply equals the demand. So if the first equation equals P and the second equation equals P, then we can set these two equations equal to each other, right? So then we'll get 60 plus 0.0012x equals 80 minus 0.0008x, right? If we add the 0008x to both sides, we'll get 0.002x equals, and if I subtract 60, we get 20, so then x is going to be 10,000. 20 divided by 0.002 is 10,000. So then when x is 10,000, I'll work over here. I'm going to use the first equation. P is going to be equal to 60 plus, if I multiply that 0.0012 by 10,000, since we have 4 zeros, the decimal moves to the right by 4. 1, 2, 3, 4, so that ends up being 12. So 60 plus 12 ends up being $72, right? So what this is saying, the equilibrium point is going to occur if we produce and sell 10,000 units at $72 each. Okay, 10,000 units at $72 each. I don't like this, and let's do one other thing. Okay. And we would just want to make sure that this order pair works in both equations, that it makes them both true and the same. Okay. And then I think we have a typed version of what we just did. You see it here. I got x equals 10,000. And then when x is 10,000, the price should be $72. And this point should satisfy both equations. Okay. And with that, that concludes the last of the new material. We have about 5 minutes left on the clock for us to finish at the same time. But since it's the last lecture, if there aren't any burning questions, I'm going to let you guys go. Okay. Have a safe evening.
Question.
Go ahead.
Is there a homework lesson this week?
Yeah. The last should be 6.4, right? So it should be 3.1 and 6.4.
And the test opens up tomorrow?
Tonight. Yeah, tonight at midnight. Exam 3 is over 2.1, 2.2, and 2.3. And then I'm going to have to get back to you about the final exam.
Okay. Right.
Okay.
But just to clarify, so the homework is 3.1, right?
3.1 and 6.4. That's 6.4 is the last of the semester, the last of the new material.
Okay.
Is it not on Pearson?
No, I think it is.
Okay. Any other questions, gentlemen? Okay. If there aren't any other burning questions, you guys have been awesome. So these last couple of days, we'll use them as study sessions and review. I mean, the main thing that you need to do with me is just check in on a daily, like whenever we meet, just check in. And then, if you really are interested in the review, you don't have to stay. I'm not going to make you stay. The main thing is you just need to check in. But we'll meet and kind of work through examples. We have about 4 meetings left, Thursday and Friday, and then Monday and Tuesday. And then after that, it's just going to be the final exam. All right? Enjoy the rest of your day. See you guys on Thursday. Stay safe, and I hope your candidate wins. Okay, take care.